Okay, as I'm recording this, I'm not sure if this is going to be part of day 7 or day 8 because I actually haven't looked at how long the video is for day 7. But it'll show up on the play pause it title. So, implicit differentiation. All of the functions that we've dealt with so far have involved one variable defined explicitly in terms of another variable. They have all been y equals. Okay, that was the video I just finished. They have all been y equals, okay? So we've seen, just to keep it simple, we've seen y equals x squared. We know how to take the derivative of that, keeping it simple. An implicit relation is something where it's not y equals, like these two examples. In the first one, we could solve for y, right? Subtracting the x squared and then taking the square root of both sides. And then we could differentiate the way that we normally do. I'm not going to take the time to do that because you guys can practice chain rule with that if you'd like. But in the second one, there's no way to get the y completely by itself. If I have, I'm getting ahead of myself. Okay. I just blew the punchline on this. We need the chain rule, right? We need the chain rule to differentiate that because we have a function inside of another function. Okay. So in the second one, we can't solve for y to get an explicit relation. Like if we wanted to solve this for y, maybe a strategy would be like, okay, get the y's. There's this fly buzzing around me and it's like right by the iPad. I'm wondering if you could hear it buzzing. Okay, get the y's together, but then what? Take out a y? But then what? Like if I want to get, did I do that right? No. If I want to get the y by itself, now I still have a y on both sides. So there's no way to get this to be explicitly y equals and then x on the other side. Okay? So we need implicit differentiation for this. I'm gonna leave it at that. I'm gonna show you down here what implicit differentiation is. So we need the chain rule when we're differentiating this with respect to y. So let me show you. I'm gonna make this a little bigger. All right, I know the derivative of x squared is 2x minus. Now we've never taken a derivative of y before, or at least we've only ever written it as like y prime or dy dx. But this is more than just y. So I need to take the derivative using the power rule, just like I did on the x. But then I need chain rule. So what we're thinking of is, we're thinking of that as like a y squared where, let me see if I can remember the colors. I don't know if this is going to be color coded the same, but take the derivative of the outside. So there's an invisible one right there. Leave the inside alone and then multiply by the derivative of the inside. That's what we're doing. Now, technically, so let me show you this in a different way. Derivative of the outside, leave the inside alone, and then take the derivative of the inside, right? Remember that d over dx means take the derivative of the thing that comes next. Well, now look, if I put this over 1 and I multiply it like a fraction, it becomes dy over dx, right? So that's where I got that under a. Now, let's do the same thing for the x. Let's pretend it's a chain rule problem. Take the derivative of the outside, leave the inside alone, and then multiply by the derivative of the inside, right? If I do the same thing, put this over 1 and multiply it, I end up with dx over dx, and anything divided by itself is just 1, so that's where the 2x comes from, okay? So, and then from here, now I can solve for dy dx. So I'm going to make it so that this is positive. So kind of adding it to the right and then flipping. And then I can divide. And then I can cancel. My derivative has a y in it. That's what's going to happen oftentimes, or almost all the time, with implicit differentiation. Our previous derivatives never had y in them. Okay, so I'm going to show you, where do I want to show you this? I'm going to show it with this one. Okay, don't write this down. I'm going to go, excuse me, I'm going to just take the derivative of this and I'm going to forget the chain rule. Okay, I want to show you what happens if you're on a quiz or a test and you just completely forget the chain rule. So I'm going to use the power rule plus I'm going to use the product rule. So let me color code this. The derivative of this is leave the first alone, derivative of the second, plus leave the second alone, derivative of the first, equals the derivative of 1 plus, again, the product rule. Leave the first alone, derivative of the second using chain rule, right? So the derivative of e is e, leaving the x squared, which is the inside alone, and then multiplying by the derivative of the inside. Plus leave the second alone, derivative of the first. Well, if we're saying that x is the same as y, then the derivative of y is 1. Now you're looking at this and you're like, wait, what were the directions again? Find dy dx. There's no dy dx. So hopefully when you get to this point, it triggers in your head, oh, wait a minute, I was supposed to use chain rule. So when I take the derivative of this first thing, 5y to the fourth, I then need to multiply by the derivative of the inside, which is y. The inside is y, so the derivative is dy over dx. And then let's see if I can just fix this. When I take the derivative of this thing, is that the right color? I don't even know. Yes. So I left the first alone and I multiplied by the derivative of the second. That involves a y. So I need a dy over dx. Notice that this one does not involve a y. When I leave the second alone, take the derivative of the first, it doesn't involve a y. So I don't need to do the derivative, or the chain rule, maybe I should say, because this is what's going to happen. If I did the chain rule, it would just be 1, okay? And then in that green, I left the first alone, derivative of the second, plus leave the second alone, derivative of the first, and then using chain rule. Okay, and then from here, it's pretty simple algebra. So probably pause me and take a minute to soak all of that in. All right, so I'm going to get all of the things that have a dy dx on one side. Let me see, did I get everything? Yep. And then all of the things that don't on the other side. Then I can factor out a dy dx. You're probably not, whoa, love it when that happens. You're probably not going to need to show this much work. And then we can divide. Oops, that's an exponent. And then you should probably check and see like if anything's gonna cancel if you factor. You could take out a 2xy from the top. That's probably gonna make it look a lot neater actually. 2xy, and then I'm left with what? E to the x squared minus y squared. And then from the bottom, I can't do anything. So that actually didn't really do a whole lot. I would accept either of these answers on the bottom line here. Okay. Okay, let's see. I'm gonna say, let's skip C. Let's jump to this one so we can find a second derivative using implicit. So just to reiterate, if I'm taking the derivative of a y, I need chain rule where I'm going to be multiplying by dy over dx. If it doesn't involve a y, I don't need to do that. So power rule and then chain rule. Plus, that's basically power rule, right? If I think of it as y to the first and I'm taking the derivative of it, I move the power in front, decrease the power by 1, right? So that's power rule. The 2 is just hanging on for the ride. And then chain rule. This one doesn't involve a y, so I don't need dy dx. And then the derivative of 1 is just 0, right? So the first derivative, I think this is pretty straightforward, so I'm not talking it through. Don't make the y plus 1 magically bump up to the top when you cancel out your 2's, okay? All right, and then the second derivative, let me rewrite. I'm going to actually write this like this and use the chain rule. If you want to leave it like that and use the quotient rule, that's totally fine. I prefer to use the chain rule when I have like a number in the top of a fraction, and I can just move the denominator up using a negative. So now I'm going to be taking the derivative of the derivative to get the second derivative, right? So I'm going to go derivative of the outside. I think these are the same colors, but I'm not sure. Derivative of the outside, leave the inside alone, times the derivative of the inside. And again, just reiterating this, I've talked about this before. I think it was when we introduced higher order derivatives, which I think was day 5, but it might have been day 6. Think about if I just multiply this together. On top, I have d squared y, and on bottom, I have the quantity dx squared, and technically that should be in parentheses, but mathematicians are lazy, right? And then I've got, I'm going to just write this like this for now. Again, thinking of this, I just talked about this, over 1 and multiplying straight across, we've got dy over dx. So we're going to take that dy dx equation. I think I'm going to use a highlighter. We're going to take the dy dx equation right here and sub it in right there. I don't know what you guys are doing. I'm wondering if using the highlighter is messing you guys up in your notes, because then you can't color code it. All right, so that's the second derivative using implicit differentiation. So write yourself a note. You're always going to sub back in for the dy dx. Always, 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 always in the second derivative. All right, I think this is the end. Okay, so for the function, blah, 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 find dy dx using implicit. So I'm going to write it like this first. This does not involve a y, so I don't need chain rule. This does involve a y, so I do need chain rule. Super duper common mistake, and I'm 100% sure I'm going to make it at some point when we're doing implicit differentiation. Oftentimes we get so caught up in the chain rule and the like, when do I do this and when do I do that? We forget to put a 0 at the end and we leave a 4. Remember, the derivative of 4 is 0, the derivative of a constant, right? So I'm going to move some things around, or one thing. And then I'm gonna divide by 1/2 to get rid of that, or multiply both sides by 2, however you want to think of it. And then I've got negative x to the negative 1/2 over y to the negative 1/2, which I don't like negative exponents, so it's gonna flip. And just to make it look nicer, I can write it as, let's hold off on this because we're going to compare this to something. I want to wait and see a minute. Okay. B says solve the equation explicitly for y and then differentiate. So in B, I'm still going to start with this. I'm going to get the y by itself. I'm going to square both sides. So I'm going to have, do I want to multiply this out? It's probably going to be easier if I multiply it out. So it's going to be, is that right? The outer and the inner are both minus 4x to the 1/2. So when I add them together, I get minus 8. And the last times last is x times x to the 1/2 times x to the 1/2, or negative, I should say. When I add those exponents, I get x to the 1. So when I take the derivative of this, derivative of 16 is 0. 8's hanging on for the ride. Move the exponent, or move the exponent in front and decrease the exponent by 1. And then the derivative of x is equal to 1. So I have something like that, right? Now, check that your solutions to part A and B are consistent by substituting the expression for y into your solution for part A. So they want me to take this and substitute it in right there, and then it should match my other solution. So let's do that.